Hello, everyone. I'm Artem Golovatiuk from the University of Naples, and I'm going to talk about the direct detection of dark matter experiment on behalf of the NEWSdm collaboration. NEWSdm stands for Nuclear Emulsions for WIMP Search with Directional Measure, which is a collaboration of 14 institutes and 80 scientists of multiple countries that you can see on this slide. Basically, the goal of the experiment is a direct detection of the WIMP recoil with ordinary matter, the detection of the track of recoil nuclei. Since we have the nuclear emulsions both as the target and the detector, we can see the track of that recoil nuclei leaves in the emulsion, and this allows us to see the direction of the track, which is important as it can go beyond the neutrino floor, which is the area in the parameter space of potential WIMPs where isotropic neutrino background comes into play, and directional detection can identify signal from the isotropic background. Nuclear emulsions has been around for quite some time and took part in important discoveries such as discovery of pion or new mu to new tau oscillation recently. But this particular type of emulsions that we are using is developed in a Japanese part of our collaboration. It's called nano-emulsion imaging tracker, and the peculiarity is the very fine, the very small size of the crystal grains. So the emulsion itself consists of silver bromide crystals in organic gelatin, and the recoil nuclei leaves track of excitated grains, which are then further developed, chemically developed, and the fixed silver filaments remain in the place of the track, while all other silver bromide crystals are dissolved. The important part of the studies and research and development in our experiment is dedicated to going beyond the optical resolution, since the data from the detector needs to be scanned. So the tracks needs to be scanned with optical microscope, as it's much faster than an X-ray or electron microscope or any other alternative. So the optical microscope is very fast, but most of the tracks of interest go in the for the WIMP recoils are expected to go in the quite short track lengths, so order of hundreds nanometers, and in that track range we can't distinguish with default setting of optical microscope. So if several grains, as you can see on the image on the right, if several grains are located closer than the optical resolution, you see one peak, one blob. So one brightness cluster with one peak that can't be distinguished and can't be distinguished from a single grain. So you can't say that whether it's a track that consists several grains. So one of the approaches that are being used and developed is the shape analysis, which takes an elliptical fitting of the pixel cluster. And for that elliptical fit, we can see that the ellipticity correlates with the track length, so with the distance between grains in the track. And by applying the ellipticity cut, we can pre-select longer and longer tracks that we are sure that correspond to several grains, not one grain. So what is the problem with one grain is that simple thermal fluctuation in the crystals can cause single isolated grains to get excitated, and then during chemical development they become event-like particles. So they become event track-like events, let's say, but they consist only of one grain, while track of the recoil nuclei consist of several grains that got excitated when the nuclei passed. Another important physical process that is allowing us to go beyond the optical resolution is localized surface plasmon resonance, which is basically the effect that the reflected light, the brightness of reflected light, depends on the internal structure of the crystal for silver and gold nanoparticles, and it depends on the wavelengths of the falling light and on the scattered light and on the polarization. So basically, we expect, and so it is expected for larger crystals to give a resonant peak on larger wavelengths, so more red scattered light, and also for the light polarization rotation, when the light polarization is aligned to the major axis, it behaves as a larger particle, so the reflected light is shifted to the red, and if it's the polarization is aligned to minor axis, it's shifted to the blue. For monochromatic light, this would mean that if we have several grains randomly aligned within the track, when we rotate the light polarizer, different grains will have resonant peak on different polarization angle, which can be seen here on the experimental images from the emulsion. So in each row, the first image is obtained with unpolarized light, but when we apply the light polarizer and rotate it, we see that the brightness peak moves. So there is an evolution of brightness peak. If we follow the barycenter of the brightness of the cluster, we see that the barycenter moves, and with that movement, we can first of all estimate the distance between grains in that track, and also we can estimate the angle, so the direction of the track, so in which those several grains are located. Also, so here are the experimental results examples for the non-monochromatic but white light with color camera in the microscope. So you can see here that, as I mentioned before, so when we have polarization angle aligned with the major axis, the reflected light is shifted to red, more red, orange, or well, so for the smaller nanoparticle on the left, it's more green because the nanoparticle itself is smaller. But when it's aligned to the minor axis, the reflected light is shifted to blue. So this can also be used to probe internal structure of the track of several grains. The other important thing is that, so while we can use GANT4 and other Monte Carlo simulations to simulate the recoils in the emulsion, to simulate the track formation itself, the optical image formation was not available. So the simulation of optical image formation. For that, we developed an algorithm using the discrete dipole approximation, and so the implementation called ADDA. You can see here the corresponding link, and HoloPy is a Python package that uses discrete dipole approximation and can take different parameters of the light beam, can take basically, you can define any structure of the object, and you can obtain the reflected light, including the Plasmon resonance effect, and also it allows to simulate the microscopic length. Here are several cross checks for simple objects. For instance, for silver spheres, we see that a larger sphere have the resonant peak shifted to the right, so to the more red light. And for 100 nanometer, we also see the quadruple resonance, so the second peak, as was mentioned on the previous slide, so on the plot on the previous slide. For the silver ellipsoidal particle, we see that while with rotating of the light polarization, so the major axis gives resonant peak on longer wavelengths, and minor axis, so when light polarization is aligned with minor axis, it gives shorter wavelengths. This is an example of the image, so the microscopic image simulated for structure of two filaments, which is represents the experimental track. So the possible simulated experimental track. And here you can see, as expected, the brightness peak of the image shifts between those two tracks with the polarizer rotation. So for analyzing the data from the optical microscope, so first of all, we are using several approaches based on machine learning, mostly on convolutional neural networks, as we have image data. So first of all, we want to reduce the background. As I mentioned before, there is a contribution of random thermal fluctuations called fog. So they are being also reduced by reducing the temperature during the exposure, that I will mention also further when I will talk about the test run and plans for the experiment. But anyway, we need to have several reduction techniques. So one of them is machine learning based. And here we also compare it with a simple cut-based approach on the barycenter shift analysis. So for the polarized images, we can study the evolution of the barycenter of brightness in the image. And so take the events with longer shift that correspond to longer tracks. And so while we get similar signal efficiency for machine learning and cut-based approach, but the background reduction is orders of magnitude, so several orders of magnitude higher. Here we use emulsions exposed to carbon beams with fixed energies of 1300 keV as so they used to simulate signal events. So they used to simulate WIMP recoils. Further, we are going to take a combination of carbons in order to simulate WIMP of specific mass. So another approach is that using the effect of Bragg peak in the emulsion for the recoiled nuclei. So we expect that nuclei will release different amount of energy in the beginning and in the end of its track, and therefore the ionization will be different, and we expect that the crystal size, so the grain after the development can be different, and therefore with color camera we can identify that with the plasma resonance, so that the resonant peak will be on with different colors, let's say, and use machine learning for the head-tail identification. Currently, the prediction accuracy is about 65% on validation data, so on the data not used during training. However, the training accuracy itself is quite high, so there is a room for improvement, and so the research is ongoing. And one more application of machine learning is reconstruction of Z positions of the grain, since to reconstruct with high precision during the scanning, we need to take a large number, so about 5 or 7 images on different depth of the during the scanning to identify that coordinate of the grain. While there is a project of the next microscope that will be able to take simultaneously images on 2Z coordinates, but by default it will still have accuracy of about 400 nanometers. While by applying the convolutional neural, so by applying machine learning prediction for the Z coordinate, we get accuracy of about 46 nanometer, which is order of magnitude higher. And this would allow us to speed up the scanning, and machine learning processing itself can be done offline later. So currently, we are processing the test run, which took about 10 grams of emulsion for more than a month in the laboratory of Gran Sasso. Here you can see the installation of the shield. So it takes the polyethylene shield, and inside of it is 10 centimeter of lead, and inside another 20 centimeter of polyethylene to further shield from environmental radiation. Yeah, and so currently also you can see here the refrigerator, the cooling system, which is important, as I mentioned before, first of all, to reduce the thermal fluctuations, but also the lower temperatures reduce the sensitivity to electrons, which correspond to the background, since so we don't expect beam signal from electrons, but they are internal part of the, so the carbon 14 contamination is internal part of gelatin. So currently there is some contribution of the background induced by carbon. However, there is also R&D in process to exchange gelatin to synthetic polymers, which would erase that contribution. Also the research is, so the work is ongoing on lowering temperature even further. The next step is minus 80 degrees Celsius. But currently with this exposure, we are going to quantify the approaches that we have. So the background reduction techniques that I mentioned previously, the analysis. So this is all currently ongoing. So the exposure and the development of the emulsion films is finished. Right now, we are scanning them and applying the analysis. The first big goal of NEWSdm experiment will be a 10-kilogram target, which is expected to probe the Dama Libre region, which is an important first step. But further, with improving the sensitivity and the exposure mass and time, we hope to achieve the neutrino floor, so the isotropic neutrino background. And in that region, NEWSdm will be significant. So we will have a significant feature as it can see the directionality. Thank you all for your attention. And any comments and questions are very welcome.